Welcome to our next lecture in the series on condensed matter theory. In this lecture I want to discuss a single impurity in an otherwise perfectly periodic lattice. And in order to simplify the mathematics, I will look at a tight binding Hamiltonian with only nearest neighbor interaction in a one-dimensional chain. And I will model the impurity by just changing the onsite interaction on the side where I have my impurity. So of course when you exchange one atom with another, many more things than just changing the onsite energy might happen. You can get changes also in the hopping integrals. You get strain, so the atoms might shift a little bit so that you have a slightly longer range effect. But all of those effects can be treated with a method that we just discussed here. Everything is going to be very similar. The only thing is that it's just more involved and elaborate. And you have to look in three different directions, take in bigger matrices for your interactions. But none of the essence will change. So we will look at a single impurity in a lattice, and we will do this following the example where we have our bare Hamiltonian of a perfectly periodic lattice, where we have our lattice sides going from minus infinite to infinite, an onsite energy, A dagger J, Aj, plus an hopping term. We will assume that we have a basis of S electrons, where we can hop to sides J plus 1 from side J, or we can hop from side J plus 1 to side J. Then we'll put an impurity in that perfectly periodic lattice. And we will put that on side J is equal to 0. So on side J is equal to 0, the onsite energy is not epsilon s but epsilon s prime. So H1 is epsilon s prime, A dagger 0, A0. And then we have to realize that we still have the energy epsilon s in H0. So we'll have to subtract epsilon s from our Hamiltonian. And our full Hamiltonian is now given by H is H0 plus H1. H0 we can easily diagonalize with the use of a Fourier transform, which allows us to calculate all the Green's functions because we know the eigenenergies in k-space, and we can just sum 1 over omega minus epsilon k for the Fourier transform or for the Green's function in k-space, and then sum it e to the I kr for the Green's function in real space. But if we try to diagonalize the full Hamiltonian by a Fourier transform, then we'll see that this doesn't work. So the trick that we used so far to diagonalize by a Fourier will not work. So if we look at A dagger R is square root 1 over V, sum over all states in k-space, e to the minus I k dot R, A dagger K, and we insert this in our Hamiltonian, then we'll find that H is sum over K, epsilon s plus 2 ss sigma cos ka, where a is the distance between the atoms in our system, A dagger K AK, which is H0, so H0 perfectly diagonalizes, but H1 is going to become much more involved than it was, because here it was only interacting on a single state, and it is now coupling all states in k-space with each other. It's a scattering between k and k prime of 1 over v e to the I k minus k prime dot 0, so in principle that will just be 1, A dagger k prime ak. So our local impurity after the Fourier transform couples all states in K-space with equal strength. The Fourier transform of a delta function is to constant, which is exactly what we find here, although we work not in an infinite translational symmetry, but a discrete translational invariant system. So with that, we do not get the eigenstates of a single impurity in a lattice. Now, of course, we can always make a finite system, write down the Hamiltonian in terms of a matrix and diagonalize it. But there are much more elegant ways to do this, and that is with the use of Green's functions. So our Green's function in real space, R prime of omega, tells you how you propagate when you insert a particle at site R prime to site R. For a periodic system, it only depended on the distance between R and R prime. Our Hamiltonian is no longer periodic, so now it really matters on where do you put that particle and where do you annihilate it. If you put it on the impurity site and annihilate it somewhere, you get something different than when you put it extremely far away from that impurity and take it extremely far away out from that impurity. When R and R prime are extremely far away from the impurity, you should expect that you just go back to the periodic system. Whereas when you sit on the impurity, you might see strong deviations from the original Green's function. So this depends non-trivial on both R and R prime. They're no longer periodic. And with that, we can now define the local density of states. In a fully periodic system, creating a particle on one side and taking it out on that same side is the same for any side you do this, and therefore the local densities of states is just the densities of states. Now we have a dependence on the side where we create or annihilate the particle, and our local densities of states will be defined as 1 over pi, the imaginary part of G R of omega. Where we look at the total eigenstates projected to a local site. If we look at the Green's function, where you propagate from R prime to R in the time domain, then this is minus I theta t 0 AR e to the minus I h t a dagger R prime 0. So we are truly looking on how do you propagate in your system. And if you want to calculate conductance and how your impurity changes the conductance, then this tells you how you scatter of that impurity. And we will use that later on when we not look at a single impurity but on many impurities, such that you really get scattering between different momentum eigenstates. And then we can calculate what the lifetime is of the state with a certain k vector, and that lifetime of that state in a k vector is exactly the tau, or the scattering rate, that we introduced in the Drude model. So with that we will then be able to calculate what the conductivity is due to the impurities that we have in our system. But before we get there, we want to look at the effect of a single impurity in a lattice, which has a lot of applications just by itself, which we will come to when we have the results. So we're going to use the Dyson equations. And we have our full Hamiltonian given by H0 plus H1. And our H0 and our H1 are perfectly given here. So G0 of K prime and omega is the Green's function of an infinite one-dimensional chain with a single band, and that is diagonal in K space. There's not a sum over K. 1 over omega minus epsilon K plus I0 plus, and epsilon K is epsilon S plus 2 SS sigma cosine Ka. So far so good. The Green's function of our periodic system without an impurity in real space, which can be calculated by Fourier transforming. It's 1 over V, sum over K, e to the I, K, R minus R prime, G0, K prime of omega, and this is not a K prime anymore. Well, it doesn't matter because you have the delta function. Now, what we want to know is the full Green's function in real space. And now we can use the Dyson equation, where we say this is G0, where you propagate from R prime to R, plus the sum over R double and R triple, where we have the full Green's function propagating from R prime to R triple, then the interaction from R triple via the Hamiltonian scattering to R double, and then the propagation by G0 from R double to R. If we do this graphically with diagrams, then we say we move from R prime to R, which is equal moving from R prime to R without scattering of your impurity, plus the propagation in the full system with an impurity from R prime to all possible R double primes, then scattering, and then propagating from R triple prime to R. And H1 is given as epsilon S prime minus epsilon S A dagger 0 A0. Now the fact that our impurity only acts on a single side makes this sum over all intermediate states R double prime and R triple prime of course much easier, because you only have an interaction here when both R double prime and R triple prime are equal to 0. So we have that our full Green's function that tells you how you propagate from R prime to R is equal to the propagation that we have in our bare system without an impurity, plus the propagation from R prime to the impurity, then a scattering, and then a propagation from the impurity to R by the bare Green's function. Well, we can iteratively put in our propagator with the Dyson equation such that we only have bare propagators from r prime to r, or going from r prime to 0, scattering going from 0 to r, or going from r prime to 0, scatter, go from 0 to 0, scatter, and going from 0 to r, or going to 0, 0 to 0, etc., etc. etc. We can have 0 interactions, 1, 2, 3, 4, 5, etc. And you always move to the impurity, and then you move from the impurity back to the impurity, or you move 2 times back from the impurity, 3 times. And we have to sum all those possible paths in which you can move from r prime to r. Well, what we have here is going from r prime to r without an interaction, and then going from r prime to 0, and then we have a sum from n is 0 to infinite, going from 0, scattering from 0 to 0, and propagating to 0 to the power n, having a scattering and propagating to r. This is a geometrical series. The sum n is 0 to infinite, x to the power n is 1 over 1 minus x. So our full propagator going from r prime to r is given by going from r prime to r by the bare propagator plus r prime to 0, 1 over 1 minus, scattering from 0 to 0 and propagating back to 0 with the bare propagator times scattering from 0 to 0 and propagating from 0 to r. And all dynamics now governed by H0, the fully periodic Hamiltonian, instead of H1. So these are all diagrams that we can calculate. If we put them in formula, then this is G0 r prime r of omega plus G0 going from r prime to 0 times 1 over 1 minus epsilon s prime minus epsilon s, which is H0, G00 of omega, and then epsilon s prime minus epsilon s, G r to 0 of omega. I go from r prime to 0, then I can scatter 0 to infinitely times moving back to myself. I have to scatter at least once, and then I go from 0 to r. In order to evaluate the full propagator, we have to evaluate the bare propagator propagating from r prime to r. So we are interested in the full propagator from r prime to r, and we need, in order to calculate that, the propagator from R prime to R for G0. There are two ways in which we can calculate this. One is with the use of continuous fractions, which we will discuss in future videos, because that method gives you a lot of insight on how you can work with Green's functions, how you can play with them, how you can divide your system in subsystems and connect them together with the use of Green's functions. It also relates to methods you use in renormalization group theory, Krylov subspaces, and things that you will encounter when you look at renormalization methods. So that's a nice method to calculate Green's functions. But we can also just directly calculate it via a Fourier transform of the known Green's functions in K-space. In this lecture I will write them down as Fourier transforms of the known Green's functions. We will not do the integrals explicitly, we will come back to them later when we do them with continued fractions. Because there I think they are easier to handle and give you more insight than just doing a Fourier transform of some complex function. So G0 R prime of omega is the vacuum expectation value of creating the particle at R prime, looking at 1 over omega minus H0 plus a small imaginary offset, and annihilating the particle at R. Well, we can replace the local creation and annihilation operators by creation and annihilation operators in K-space, summing both over K prime and K, 1 over V, e to the I, K dot R minus K prime dot R prime, and then we have the Green's function in K-space, and this of course gives you a delta function between K and K prime because crystal momentum is conserved, and this becomes epsilon K. So what we have here is a sum over K, 1 over V e to the I, K R minus R prime, 1 over omega minus epsilon K0 plus I0 plus. Well, I put a 0 now to show you that these are the eigen energies of your periodic Hamiltonian H0. Now we can immediately see a few properties of our bare Green's function propagating from R prime to R that we will use when we evaluate the full Green's functions and the eigenenergies of our full Green's function, or the eigenenergy of our full Hamiltonian, which is given by the poles of the Green's function. And if we look at the poles of R prime R, then the poles of our Green's function are just given by the eigenenergies of the bare Hamiltonian. And it doesn't matter if you go from R to R, where you measure the densities of states with your Green's function, or where the imaginary part of your Green's function is the densities of states, or if you go from R prime to R, the only poles that we have sit at the energies that are the eigenenergies of your Hamiltonian H0. That's one of the properties that we will need later on. And there is a minimum energy of those eigenenergies and a maximum, which defines the bandwidth of your system. Then if we look at the imaginary part of the Green's function. And we look where this imaginary part is 0. Then this is true for all frequencies that are smaller than the minimum energy of the pole, or where this energy is larger than the maximum energy of your pole. So your density of states is restricted to the energies where your Hamiltonian has eigenvalues. If your omega is smaller than the smallest eigenvalue, the imaginary part of the Green's function is 0, the densities of states is 0. If your energy is larger than the largest eigenvalue of the Hamiltonian, also your densities of states is 0, and therefore the imaginary part of the local onsite Green's function will be 0. So these are two properties that we will need to discuss properties of the full Green's function. So if we look at our Dyson equation, then that relates the full Green's function, where we propagate from r prime to r, to the bare Green's function, where we propagate from r prime to r, but now in the Hamiltonian given by h0 and additional scattering centers. The poles in our full Green's function relate to the eigenenergies of our Hamiltonian. And the poles in our full Green's function are given by the poles in our bare Green's function, because if this Green's function has a pole, our full Green's function will have a pole. And therefore we find that the poles of my full Green's function are the same as the poles of my bare Green's function. For all sites where I measure the local densities of states. So the imaginary part of my Green's function is the densities of states. That gives you a delta function whenever you have an eigenstate. And you have eigenstates whenever you have poles. And the poles of G0 are the same there. So we can conclude that we have the same eigenenergies. Unless we generate new poles. And here we see that propagating from r prime to 0, well, that's not going to give me other poles than I have there, but I have a 1 over 1 minus epsilon s prime minus epsilon s times g00 omega. When this diverges, or when my 1 minus epsilon s prime minus epsilon s g00 omega is 0, I will generate a new pole. So my eigenenergies are the same as the eigenenergies that I had before, unless 1 minus epsilon s prime minus epsilon s times the bare Green's function going from 0 to 0 is equal to 0. So this is just related to the densities of states. So we find one possible additional pole, so we find one possible additional eigenenergy, and the condition to find an additional eigenenergy is that the local Green's function has to be equal to 1 over the impurity potential. When your impurity potential is very small, 1 over becomes very big. So then the requirement is that your Green's function becomes equal to a very large real number. When your impurity potential is very small, the requirement is that your Green's function is equal to a smaller real number. But it always has to be a real number. So with that we can already rule out any frequency within the density of states. So whenever we have eigenstates for the bare Green's function, we have an imaginary part of the bare Green's function, and therefore this is imaginary, and something imaginary can never be something real. So if we find an additional pole, it will be outside of the energy window in which we had poles for the bare Green's functions. So we'll always find the same energy window in which we have poles, and we possibly find a new window or a new additional eigenstate outside that window. So if we look at our example of a one-dimensional tight binding chain, then we have our local Green's function, which we calculate from a Fourier transform. We know that r is equal to r prime, and we'll do the analytical derivation later with the use of continuous fractions. The center of our density state sits at epsilon s, the maximum at epsilon s plus 2 ss sigma, and ss sigma is negative, so I'm just going to take absolute values there. The minimum at epsilon s minus 2 ss sigma, and our densities of states for a one-dimensional system diverges at the zone boundaries and then has this shape. So this is minus the imaginary part of G00 omega. And it would be the same for any other lattice site because we are in a periodic system. Now the imaginary part diverges. The real part is also diverging, and it's negative, and then it comes back positive. And it is 0 in between. So that is the real part of the local Green's function. We now look for bound states or additional eigenstates outside of the continuum, and the equation that we have to fulfill is that the real part is equal to 1 over the impurity potential and the imaginary part is 0. And we see that for energy smaller than 2 times the absolute value of ss sigma, minus epsilon s minus 2 epsilon ss sigma, or larger than epsilon s plus 2 ss sigma, you're outside the bandwidth, and therefore the imaginary part is 0, and we have a real part, and that real part is diverging. So even for very small impurity potentials, very large 1 over epsilon s primes minus epsilon s, you will still find a solution of this equation and therefore have an additional state outside of the continuum. And of course, if we make our impurity potential larger, the inverse of the impurity potential becomes smaller, and with that the energy that you have for your additional states becomes lower, so further away from the continuum. And what the energy difference between the energy of the pole and the continuum is what we will call the binding energy of our impurity state. We can now look at the full Green's function, and let's look at the imaginary part of G 0, 0 omega. So we look at the local densities of states at the site of the impurity. when epsilon s prime is much smaller, or is barely smaller, almost equal to epsilon s, we find still a bound state, but at the same time your densities of states is going to be very weakly modified. What is not modified at all is the bandwidth and the energy at which you start, up to epsilon s plus 2 ss sigma, because that is just given by the poles of G0, and whenever G0 has a pole, also the full Green's function has a pole. But there will be one additional pole sitting slightly below. So that's as a function of frequency. Now when we make our energy larger, epsilon s prime smaller, then epsilon s will now have a clear bound state, and also the densities of states of the continuum will get modified. The energy window is still exactly the same. So the eigenenergies are still exactly the same. However, the character that the impurity side contributes to your densities of states is going to be different. And here we have a single pole. And if we make the impurity potential very strong, then of course at some point when it is infinitely strong, the eigenstate locally will just be the local state. So we have less and less contribution of the continuum into that impurity state. But the bandwidth and the band eigenenergies will not move. You can think of this, and the reason why the eigenenergies of the continuum do not change, in the sense that you have infinitely many states in the continuum. And you have one impurity. That single impurity will contribute an infinitesimal small amount of its character to each of the states in k-space. Therefore, each of the states in k-space will be only infinitesimal small changed, and therefore their eigenenergies don't really change. Now, of course, that local impurity is going to get an infinitesimal small change to its wave function from infinitely many wave functions, and therefore that local wave function, of course, will shift. We had that before. If you have two states interacting, one state will shift up, one state will shift down, such that the local character is going to stay at the same energy. We now have infinitely many states, infinitesimally small shifting down, and that gives you a finite contribution to the local state. Now, we find that we always have a bound state in our one-dimensional tight-binding Hamiltonian. And this is a peculiarity of one-dimensional systems. In our one-dimensional system, our densities of states diverges, but that is really the exception and not the rule. In a general system, the densities of states will be much smoother, and we can take, for example, here a semicircular as an example of a generic densities of states. And actually this is the endpoint of a one-dimensional chain that would have such a density of states. And again, we will derive the analytical representation once we do continuous fractions, because there it is much easier to derive this than by doing Fourier transforms and all the Dyson equations. Epsilon s minus 2 ss sigma, epsilon s plus 2 ss sigma. But for three-dimensional materials, well, you might have more structure in it, but that's really not going to change all the argumentations that I want to go through. Now, when the imaginary part doesn't diverge, your real part is not diverging anymore. And for our endpoint on a one-dimensional chain, the local Green's function has a shape like this. So that is the real part of G0, 0, 0 omega. And this is minus the imaginary part of G0, 0, 0 omega. If we now have our very weak impurity potential such that 1 over epsilon s prime minus epsilon s is large, we see that there is no crossing between our 1 over the impurity potential and the real part of our Green's function. Therefore, this equation has no solution and there is no additional pole. Only when we make the impurity potential strong enough such that there is a crossing, we will find that we get an additional pole. And this, as we'll explain in a minute, is extremely important for all the semiconductor physics and doping that we do, if it would be the case that you always get impurity potentials or impurity bound states. Then all of the physics that makes the computers with which we communicate at this point would not work. So the entire semiconductor industry works that you can make impurities without creating additional eigenstats that are bound. So when we look at our generic DOS, which is the endpoint of a 1D chain, so it's both an example of something that is just reasonably smooth, and as an example we can take the endpoint of a one-dimensional chain plus 2ss sigma. When epsilon s is almost equal to epsilon s prime, then it will be very hard to see any difference from a system without an impurity, even when you look at the side of the impurity. There is no additional bound state, there is just nothing special happening. When our impurity potential is going to be smaller, then our onsite energy for the rest of the system, but not so large that we generate an additional bound state, then we find that our densities of states is still fixed to the same energy window. There are no additional eigenenergies in our system, and the only thing that is changing is that we get a shift in spectral weight that might shift to lower energies, but otherwise the width is still completely the same. And only when epsilon s prime is much smaller than epsilon s, we will find that we have now an additional impurity bound state in our system. Now let's see if we can relate what we have here to the physics of real materials that we encounter. So one of the things that we want to do in semiconductor physics is dope our system. And the idea is that when you have atoms such as silicon, you replace some of them with either 1 electron more in the p shell or 1 electron less in the p shell. And with that you do either hole doping when the dopant has 1 electron less, or electron doping when the atom that you substitute has 1 electron more. And the idea is that with this you most and for all shift the chemical potential. So when we have our silicon, we can replace it with bore, aluminum or gallium when we have one electron less, or with nitrogen, phosphor or arsenic when you want to put in one electron more. When the impurity potential that this dopant generates is small, then indeed your densities of states is not that much modified. And what will happen is that your chemical potential will just shift because of the extra electrons that you put in or the extra holes that you put in. It will either shift to the right or to the left, depending if you dope with elements that have electrons less or an element that has an electron more. If the impurity potential would be strong, you would create one additional state. And this state will be localized. And this state will stay local and not contribute to the conductivity. It's a single state, so when you put on an electrical field, there is no way that you can just make an acceleration of this state. It will always have to hop. There is no continuous transition that you can make from this state. So that would be very bad. With this we can already understand why when we have silicon you normally wouldn't dope it with nitrogen, because the impurity potential for nitrogen is too large and therefore not electron doping the system, but making localized impurity bound states in that system. So for semiconductor physics you're looking at dopants where the impurity potential is so small that you're basically just shifting the chemical potential and not creating bound states. That is different when you look, for example, at the LED windows that you see in all churches. In those windows you have these vibrant colors that are still partly transparent. Light has to be able to shine through. But you want very clear energies where you absorb the light and other energies that are nearby where your system is still transparent. For that you need to have very localized states in energy space. If we have densities of states like this, and I can make transitions from one state that is occupied to a state that is unoccupied, and these states are very well defined in energy, then I get very clear transitions in energy for my light, and therefore at very specific energies absorption, and therefore very specific colors in my system. So these windows are glass where we put in impurities, and now these impurities have very deep and very strong impurity potentials such that you get very nice and clearly bound states. In older windows this is mostly transition metal impurities that you put in your glass that then give all these vibrant colors that you have. Putting in nitrogen in diamond also gives very nice and beautiful color centers. Many of the gemstones that we have in all their vibrant colors are because we have impurity bound states in these systems. So if your gemstone would be pure, it would be just a perfectly transparent crystal, and it is the impurities that make them so beautiful and colorful. Then there is also a clear use for these intermediate scenarios, which we will normally call resonances. If you want to make a solar cell and you want to make it highly optimized, then we can make a semiconductor junction where one part we do hole doping, one part we do electron doping. Then when light shines in, it will make an electron hole pair excitation, and so you remove an electron from the occupied densities of states and you put it in the unoccupied densities of states. And then because of this difference in chemical potential, the electron will move in one direction and the hole will move in the other direction. And then of course you can close that via a wire such that you generate a current. Now what you want to optimize in such systems is first of all the absorption. You want to make sure that every photon gets absorbed at the position where you want it to be active. And sunlight in the visible range has an energy of a few electron volts, so you want to have good absorption in exactly that energy window. The bandwidth of our semiconductors goes up to 10 electron volt, so our bandwidth is much broader than the bandwidth of the solar light that comes in. So if we can reduce the bandwidth of our system, we would enhance the cross-section. So when we put in impurities, then effectively what happens is that impurity will have a much smaller effective bandwidth, where your densities of states is much higher. So the probability to make a transition between two states at high densities of states is just much higher than the probability to make a transition between two states with low densities of states. There are just more states available to which you can make that transition. So what you can do is you can take your solar cell, which is made out of a semiconductor with a very big bandwidth. You put in dyes, which then form impurities. These impurities have a reasonable strong impurity potential. If it would be very strong, you would make an exciton. They give extremely strong absorption, which we've seen in our vibrantly colored windows. They beautifully absorb the light, but that's a local state. That will not generate an electron hole pair that then couples to the continuum and generate a current. But when the impurity potential is so weak still that you're still inside the continuum, then you enhance your local cross-section, but you still talk about states that will decay and propagate, such that you still generate your current and your electron hole pair that then flows through the wire and generates the photovoltaic current. So that's how you can optimize your solar cells, by putting in impurities or dyes into your system and have a strong impurity potential, much stronger than the dopants that you put in, but not too strong that it forms a locally bound state. So we want a resonance and not an exciton. Yeah, of course these are still very generic ways of thinking about these materials. If you go into all the details, then you have all the chemical detail that you have to discuss to really optimize these materials. But these are the basic concepts with which you can work, and where we have the effect of our impurities. For now, thank you very much for your attention. We will continue in the next lectures with some mathematical frameworks where we can work with Green's functions in terms of continued fractions, which are just really nice tools to have how you can work with these kind of Green's functions. And we'll then still have a look at a crystal with randomly distributed impurities. And then, well, we have to do the Dyson equation twice to come back to the Green's function of such a system. And then we can discuss self-energies and then also relate this to the time, the scattering time that we have in the Drudel model or the Sommerfeld model. For now, we see each other later. Stay healthy.